Welcome to video lecture on the topic of band theory of semiconductor. Myself, Dr. Himadri Sekhar, class Assistant Professor of Department of Electronics and Communication Engineering, Haldia Institute of Technology. Before go through the topic band theory of semiconductor, first of all we have to know what is semiconductor. Semiconductor. The name shows that conducting property. Semiconductor. So that's mean its conductivity is semi. It's V where at 0 degree Kelvin, 0 Kelvin it shows as a insulator, and beyond that temperature it conduct electricity and it behave as a conductor. So that's why its name is semiconductor. So few properties such as its conductivity, resistivity, temperature coefficient, and current flow. So resistivity of this type of semiconductor is in the range of 10 to the power minus 5 to 10 to the power 6 ohm meter. That is the range of semiconductor. And conductivity, it's 10 to the power 5 to 10 to the power minus 6 mho per meter. Temperature coefficient of resistance, it's a negative temperature coefficient. And current flow, the current flow in case of semiconductor due to both electron and holes. That's mean whatever we got the current in semiconductor, electron and holes are responsible for that current. So before we go through the properties of band diagram, first of all we have to know the valence band and conduction band and band gap. So valence band, as we know that the atomic structure, we know that in the last orbit, the electron state, these electrons are basically called the valence electron, and this energy level is basically known as the valence band. And conduction band, next higher energy level, that is basically empty state. This empty state is known as the conduction band. When a electron gets sufficient energy, or it may be thermal energy, it may be due to temperature, when it excited from lower band to the higher band, that's mean valence band to the conduction band, by creating a electron hole pair. During that time the current will flow. So this is the basic concept of the valence band and conduction band. So basically how to know about the, or how can we differentiate between different materials such as metal, semiconductor, insulator? How can we justify among these three, on which property basically makes them difference? First, few things: resistivity, conductivity, band gap, and flow of current, etc., etc. So resistivity of conductor, or it's maybe metal, it's less than semiconductor, and resistivity of the semiconductor in between the metal and insulator. Whatever I just told that before, the previous one slide, and the range is resistivity of the semiconductor is 10 to the power minus 5 to 10 to the power 6 ohm. For metal it's less than that, and for insulator more than that. This is the range of the resistivity. So as we know that there is a relation between resistivity and conductivity, inversely proportional. So resistivity low means conductivity high. Whatever we got in case of conductor, resistivity low, that's mean conductivity high. In case of semiconductor, in between the metal and conductor and insulator. For insulator, the resistivity high, too much high with compared to that of conductor and semiconductor. That's why its conductivity is low with compared to that of conductor and semiconductor. So band gap. So band gap is the, for conductor, valence band and conduction band are overlapped because so many free electrons are there. That's why their valence band and conduction bands are overlapped. Whereas in semiconductor, this band gap is near about 1 electron volt. So for insulator, this band gap is more than 6 volt or 6 electron volt or near about that 6 eV. It may be more than that. So that's mean it's the energy gap is too large for the insulator. That's why its property shows the insulating, not conducting. Also, it's known as a positive temperature coefficient conductor basically. That means if we plot the conductivity and temperature along the x-axis and conductivity along the y-axis, it increases, exponentially increases for the conductor. That means if the temperature is increases, so the conductivity of the metal is decreases. Whereas for semiconductor, it's exponentially decreasing. That means if we increase the temperature, conductivity is decreases. That means the electron, those who are present in the valence band, they get the thermal energy and excited and reach to the conduction band, as a result generating electron hole pairs. And finally we got the current, flow of current. So if the temperature is increases more and more, that's means more electron hole pairs are generating, as a result the increasing of current. And in case of insulator, it has a negative temperature coefficient. So these are few examples of conductors such as copper, in case of semiconductor, silicon, germanium, and for insulator we know that mica, fiber, wood. These are the examples of this insulator. We know basically semiconductors are divided in two types on the basis of their doping. So first one is intrinsic semiconductor and second one is extrinsic. So intrinsic is also known as pure semiconductor. So if I got some example of this pure, silicon and germanium is known as the pure semiconductor. Whereas extrinsic semiconductor, when few doping, what is doping? Few externally doped with that of silicon and germanium. When we dope that either trivalent, pentavalent or other atom with that of silicon and germanium, it's called extrinsic semiconductor. So a pure semiconductor, when it is doped with other atoms, it converted to the extrinsic semiconductor. So extrinsic semiconductor is also divided in two types, N type and P type. On the basis of the doping concentration, doping type, not concentration, doping type, it's divided in N type and P type. When pentavalent atom is doped, pentavalent atom means, as we know that phosphorus, arsenic, antimony, bismuth is doped with germanium and silicon, then it turned to be a N-type extrinsic semiconductor. That is N-type. When 4 valence electron such as germanium and silicon is doped with pentavalent atoms, phosphorus, arsenic, antimony, bismuth, this is turned to be a N-type semiconductor. And for P-type, trivalent atom such as boron, aluminium, gallium, indium is doped with that of silicon and germanium. This is known as a P-type semiconductor. So that's mean on the basis of a type of doping, the extrinsic semiconductor can be divided in N-type and P-type. This is the classification of the semiconductor. So in case of intrinsic semiconductor, it just a draw is there, material is very pure, it's pure, no doping is there, no other atom is there. So that is the structure of the intrinsic semiconductor. So the band diagram, the band diagram of the intrinsic semiconductor. Here the band diagram is done in two conditions, at 0K and above 0K. So what happened in 0K? 0 Kelvin. So the energy that much required to electron move from valence band to the conduction band, it's not sufficient. So that's why it can be clearly seen that no electrons is moved from here to there. When above the this 0 degree Kelvin, above the room temperature, few of the electrons are getting the thermal energy and they excited and reach to that valence band to the conduction band. So that's mean in 0 Kelvin, this intrinsic semiconductor can behave as a insulator, and above the room temperature, it behave as a conductor. So the for in case of extrinsic semiconductor, so basically pentavalent atom or trivalent atom is doped with that of pure semiconductor, silicon and germanium. So when pentavalent atom is doped with 4-valent silicon or germanium, excess electron is there. So in case of n-type, so the majority carriers are electron. Whereas for p-type, when 4-valence electron of silicon is doped with trivalent atom, boron, aluminium or gallium, so there is a free space is there. Free space means a hole is created. So for p-type, holes are the majority carriers. So this is the band diagram for p-type and n-type semiconductors. So as we know that already we have known from this previous structure that for n-type semiconductor, electrons are majority carriers, and for p-type, holes are majority carriers. So that's why the energy band diagram for n-type semiconductor, the Fermi level is towards the conduction bands. So towards the conduction means it can say that the concentration of electron is higher. For pure semiconductor, the Fermi level is the middle of the valence band and conduction band. In case of n-type semiconductor, as the concentration of electrons is higher, so that's why the Fermi level is towards the conduction band. So from this band diagram, we can say that this is a n-type semiconductor, or we can say that there is a concentration of electron is higher in case of n-type. For p-type, the Fermi level is towards the valence band. So that means here the concentration of hole is higher. That's why the Fermi level is towards that valence band. And this is a band diagram of a p-type semiconductors. So finally, we just compared the band diagram of three intrinsic, extrinsic, n-type or p-type. So for it is clearly seen that for intrinsic semiconductor, the Fermi level is the middle of the valence band and conduction band. Whereas for n-type, the Fermi level is towards the conduction band, and for p-type, the Fermi level is towards the valence band. So that's why it's clearly seen that the concentration of electron and the concentration of hole make it different concentration of, and its Fermi level also changes. So why is doping is required? Basically to increase the conductivity of the semiconductor. That's why doping is much more essential and it is required. So on the basis of the type of the dopant, pentavalent and trivalent, the semiconductors are divided in two types. It's p-type and n-type. So this is the basic difference of these two type of semiconductor, intrinsic and extrinsic. Basically, intrinsic is also known as, we know that, pure semiconductor, and extrinsic, impure semiconductors. Some dopant is added with that of silicon and germanium. It makes the extrinsic type. So electrical conductivity, if we talk about the electrical conductivity of these two types, electrical conductivity is low for this intrinsic semiconductor, whereas for extrinsic semiconductor, electrical conductivity is high. Also, dependency of temperature. Both are depends on the temperature. In intrinsic type and extrinsic type also, they also depends on the temperature. For extrinsic type, it is depends on the temperature as well as the amount of impurity. So extrinsic type depends on temperature as well as the amount of impurity type. So in case of intrinsic, no impurity is doped. In case of extrinsic type, trivalent and pentavalent atoms are doped with that of pure semiconductor. And these are direct band gap and indirect band gap semiconductor. This is also type of a band gap. Direct band gap means, what do you mean by the direct and indirect band gap? So if I see that the maximum of the valence band and minimum of the conduction band. So the band gap represents the maximum energy difference between the top of the valence band and the bottom of the conduction band. However, top of the valence band and the bottom of the conduction band are not generally at the same value of momentum. Electrons are getting from here to there in a same momentum. That is the direct band gap. That is happened only in case of direct band gap. For indirect band gap, the electrons are from maxima of the valence band to minima of the conduction band. Electrons are moving in a different momentum. Okay, it's not moving in a same momentum. What happens in the direct band gap semiconductor? So, for this is the basic difference of this and the basic of the direct band gap and indirect band gap. And finally, thanks for